sorry to go over. I didn't expect to do that. I didn't expect to do the
Check, check. Okay.
Good.
Yeah, I think it's working. Okay. So, hello everybody. Thank you for coming. This is my first time presenting in the RTC conference, so I think I need to allow me to present myself. My name is George. I'm a PhD student at the University of Strasbourg, and I'm also working as a senior software engineer at Atlassian in Emil Ivov's team. Some of you may have, well, for sure, will have heard his name. I'm mostly working on the Jitsi Videobridge and Jitsi Meet. Those are in the congestion control and adaptivity features of the Jitsi Videobridge. Please do not use this web address. I was hoping I could share that with you, but it's not accessible through the Wi-Fi here, so don't do that. Yeah, let's get started. Before we get started, I would like to present, to say a couple of words about Jitsi Meet, our open source stack, what we run meet.jit.si on. I would like to share some information about meet.jit.si, which is a service that uses the open source stack to provide video conferencing, a video conferencing platform, and some metrics for our meet.jit.si service. So we are going to talk about WebRTC. We are obsessed with quality, so we are going to see what we can do to improve the quality of service and the quality that we are providing to our users. Specifically, we're going to talk about dynamically switching between one-to-one video conferencing and group call mode, and what happens if we don't, and why it's important to do it. So about the Jitsi Meet stack, we have client-side applications, 2 of them. One that runs on the browser, and it uses the WebRTC JavaScript APIs that Bernarda Boba has presented yesterday during the WebRTC tutorial. And we also have another client that runs on the mobile, and it's built on React Native. It uses React Native WebRTC. On the server side, we have the main components that we have. We have multiple components, but the main ones are Jitsi, which is our signaling server, and Jitsi Videobridge, which is our SFU, the media server. SFU stands for Selective Forwarding Unit. We also call it the bridge. I'm going to be using all these terms to refer to the Jitsi Videobridge, our SFU, throughout this presentation. For the signaling path, we are using XMPP, provided by Prosody, which is an XMPP server written in Lua. And for the media path, we use UDP, DDLS, and SRTP and God forbid TCP, as is mandated by the WebRTC standard. So this is what it looks like. Here you can see, this is a screenshot from our daily stand-ups. You can see Yana. She's on stage, and she's being received by the specific endpoint at 720p at 30 fps resolution. So it's the highest resolution that we can achieve right now. And on the horizontal thumbnails bar, you can see some of our colleagues. You can see Pavel. Well, first you can see a participant that doesn't share his video, then Pavel, Boris, Christo, some of our, and those participants are streamed in 180p resolution and 7.5 fps. So their reduced, their resolution is reduced to fit the specific thumbnails. We have multiple layouts. Jitsi Meet supports multiple layouts, so you can have the horizontal, the thumbnails bar at the bottom, the horizontal thumbnails bar at the bottom. You can have it on the sides in vertical positioning. And we recently have released a Brady Bunch style layout that presents you all the participants on your screen and take approximately equal size. We have a lot of other features that are not relevant for this measurement, for this presentation. We have video quality sliders, audio-only mode, speaker stats, transcriptions, recordings to Dropbox. We have a bunch of stuff that we are not really going to talk about, but you're free to go on our website and just, or maybe even use our service and explore what we have. So this is on the, so about the other main component that we are using is the Jitsi Videobridge, our Selective Forwarding Unit, or SFU. It has, it implements conferencing features such as simulcast and last N. For those of you that are not familiar with these terms, most of you should be, but just as a reminder, simulcast is when an endpoint encodes and sends multiple versions of the video stream that it's sending so that the bridge is able to forward the appropriate stream to the appropriate receiver. For example, Jana, in the previous slide that was on stage, we want to forward the high quality stream, 720p at 30 FIPS, and for all the other participants, we want to forward 180p at 7.5 FIPS. We also support last N, which is the bridge selects the last N. N is a number like 2, 3, 4, 5, or 10, or this is adjustable. The last N active speakers. And this is again to save bandwidth and optimize the user experience. For the participants. We also have the protocol that we're using to communicate with the Jitsi Videobridge is XMPP. We also have a REST API, so you're not bound to use XMPP if you don't like it, or if you don't want it, or if you can't integrate it. We have call-stats integration, call-stats.io, and the same applies for the Jitsi Meet client that we showed in the previous slide. So a few words about the video conferencing platform and system that we used for this, that we performed this measurement study on. It's the Meet.jit.si cloud. This is not open source. I forgot to mention the previous projects are all open source. That's why you have the banner "Fork me on GitHub." The thing that is not open source is it's our cloud infrastructure and how we scale to provide a video conferencing experience. So we do that. We scale horizontally using shards. Every shard has all the components necessary to serve several conferences. So it has all the signaling components, prosody and GCOFO. It has an auto-scaling group of SFUs. So just in case there's a lot of traffic driven to a specific shard, we increase the number of SFUs that live in that specific shard. So we deploy on multiple regions. So we have a geographically distributed cloud. We deploy on North Virginia, Oregon, Ireland, Australia. Those are our main regions. And we have multiple shards per region and an auto-scaling group of turn servers in order to support one-to-one call modes in case the direct connection fails to establish. All this is behind an HA proxy cluster, which is geographically distributed, and its purpose is to drive participants of specific rooms to specific shards. So a conferencing room lives in a specific shard, and all the participants are driven to that specific shard. And the choice of where a room lives, whether it's in North Virginia or Oregon, it's determined by the first participant. So if the first participant is close to North Virginia, he's routed there. We have C4X larges for our SFUs and the turn servers. They have high network performance, and they have plenty of CPU and RAM. So a few words about our service. This past month, we crossed the 90,000 conferences. This makes for about 3,000 conferences per day. We have a little more traffic during the week. We have a little less traffic during the weekdays, the weekend. The average conference duration is 38 minutes. Average participant count, about a little bit more than 3 participants. So we have plenty of 3-way calls. All this sums up to 3.5 conferencing minutes, or a little bit more than 7 million participant minutes. The average RTT is a little bit below 300 milliseconds, and the average upload is around 1.1 megabit, and the average download bitrate is 500 kilobits. Now, this is highly asymmetric, and we can explain this again. This is explained by the use of simulcast. So if a participant is streaming 1.1 megabits per second and simulcast is activated, you're going to have, well, at that specific threshold, 1.1 megabits, you're going to have two streams that are being streamed, one 180p stream and one 360p stream. So the participants, the receivers, are not going to get all of that. They're going to get just either the 180p stream or the 360p stream. So typically they receive less than that 1.1 megabit per second. So this explains the asymmetry in the average upload and download bitrate. We're going to break down all this information later in the results section. So this is just an overview of our service. So peer-to-peer for one-to-one. Here we're going to see why this is important, what this does. We're going to talk briefly about some related concepts such as congestion control. Hopefully we're going to be able to motivate this work and why it's important to have it. We're going to precisely define it. Group call versus one-to-one call mode, what features get activated and why it's important to deactivate conferencing features in one-to-one call mode. We're going to see other implementations. Big players have been implementing this. We're going to see who does it and who might do it in the future. We're going to overview the Jitsi Meet implementation, what we have implemented in our projects. So congestion control, now I'm going to limit myself in just one slide. This is a huge topic. I'm not going to talk about, like, it's 40 years of research and experience. We're going to limit ourselves, well, myself, in what's related and relevant for this, for the measurement study. Our service uses the Google Congestion Control, which is baked into the WebRTC engine. This is a feedback control algorithm. It takes information. The input is the packet loss and the packet delay variation. There are several proposals in the RMCAT, in the IETF RMCAT working group for other algorithms to either replace or work along the Google Congestion Control algorithm. The basic idea is, so the reaction of the GCC, which stands for Google Congestion Control, is so it has an additive multiplicative, additive increase, multiplicative decrease reaction to loss, and so this is how it reacts to loss and how it reacts to packet delay variation. Basically, if you have a positive packet delay variation, that means that you're filling up the network, queue, so you're causing congestion and you need to back up. And if you have negative packet delay variation, the network queues are being emptied, so you can ramp back up. It's not as simple as that, because you may decide to use some part of bits for forward error protection, and also you want to avoid situations where you have a stale queue, and basically the packet delay variation is zero, and you don't know what's going on. Is it because the queue is completely full, or is it because you're underusing the queue? So it's a complicated algorithm, very interesting to read about. The algorithm is implemented both in the browser and the SFU. So we have our own Java implementation in the SFU, and this may, so it's not necessarily exactly the same that runs on the browser. So we have seen, I didn't explain the picture that we have here. So basically the sender is sending, let's say 2.5 megabits per second. The receiver is recording packet arrival times and packet loss, and it sends it back to the sender. This is through standard RTCP mechanism and packets that are being exchanged on the network. Through the packet arrival times, the sender is able to deduce the packet delay variation, and through the mechanism that I just described, it adjusts the target bitrate to match the bandwidth estimation that is produced by the algorithm. So this is working nicely in one-on-one calls where the sender can shape its bitrate and adjust its target bitrate to match the bandwidth estimation. However, in a group call, the SFU, well, we're using an SFU, so we're not doing any transcoding. We cannot, and we do not want to transcode the stream in order to match the bandwidth estimation, so we need to employ other techniques in order to adjust the egress bitrate of the SFU. So we have features such as simulcast that I described a couple of slides before. So the sender is encoding and sending multiple versions of the same video stream, low quality versions and high quality versions of the video stream that it's sending. This is costly and wasteful if you're not in a group call, because it requires more CPU and more bandwidth on the sender. So for example, this is sort of hard-coded right now in the WebRTC engine, and it's not configurable, but right now what happens is if you enable simulcast, you have 3.2 megabits per second target bitrate if everything on the network is smooth, if you enable simulcast. And if you don't enable simulcast, the maximum bitrate that the sender is achieving is 2.5 megabits per second. So we have 700 kilobits that are wasted if you enable simulcast in the one-to-one case scenario. So it's important. So if a video conferencing provider wants to be optimal in terms of bandwidth usage and user experience, it needs to be able to distinguish between these two cases and dynamically and transparently switch between these two cases throughout the life of the conference as participants join and leave the conference. So other implementations. First, it was announced by Google. Google Hangouts has this functionality. It announced it in February 2016. We implemented that. We actually released it on July 2017, so a little bit more than a year ago. Slack Video announced it. Well, actually, they mentioned it during ComCon in London a few months ago. We don't really know whether they were using that even before that. We don't know whether Facebook is doing something like that, Skype and Apple FaceTime now with their group calling functionality. But given that the impact and the infrastructure pressure reduction is so significant, we believe that at some point they will have to, if they don't already do it, they will have to actually take into account this dynamic switching and implement some version of it. So this is our implementation, how it works. In this diagram, we can see the SFU and two participants. The participants join a call always in group call mode, because this is faster to be established and it's more reliable to be established. So they always enter in group call mode. And if at any time during the call the participant number drops to 2, we enter the one-to-one mode where a new peer connection is established, the WebRTC peer connection is established, and once that succeeds, once a connection is established and we have media flowing, we update the UI to move the audio and video tracks to the new peer-to-peer peer connection. If the participants increase and we go to 3, 4 or more participants, we fall back to the group call mode. We tear down the one-to-one mode connection, and we fall back to the group mode connection, and all the features, simulcast, last end, are being maintained and resumed. So results. So we compare measurements from 2 periods, the pre and post, peer-to-peer for one-to-one. This is when we actually, before we activate, after we activate this extension, we are gathering stats on the client side using WebRTC Statistics API. We push these statistics to Splunk, and from there we export it and treat it and process it. For the server side, we have Datadog monitoring. This is a server-side resource utilization monitoring service. So we have got, for the infrastructure, we have gathered data about how much the transferred data, the amount of transferred data, the SFU I/O stats like memory, CPU, system load, and things like that. And on the client, we have, for the quality of service, we have RTT, call establishment time, and download and upload throughput. So we're going to see the results now. Before we activate the extension, we gather data for 2 weeks. This is for a little bit more than 23,000 conferences, which amounts to a little bit less than 700,000 minutes. And 2 weeks, and we compare it to the period 2 weeks after we enabled the extension, and so we have almost the same amount of conferences, less than a very small change there, and the same amount of conferencing minutes. So we have 78%, almost 78% of the calls of the conferencing time is spent in one-to-one calls, and the rest is three-way or more. So it's a very important use case. So the transfer data. So in this graph, you can see the blue graphs represent the pre-activation period, and the green graphs the post-activation period. We can see that we have reduced our downstream, like the data that reaches the SFU, by almost 50%. The data that go out of our infrastructure have been reduced by 55%, and the combined, the total amount of transfer data has been reduced by 52%. So this is a significant reduction in the total costs. So about the SFU I/O, we have the pressure in our infrastructure has been greatly reduced as well. The memory we now use 35% less memory, 32% less CPU, and the system load across all of our bridges has dropped by 46%. So it's a significant reduction. Now about the round trip time, here we see, in this graph, we see the cumulative distribution of the RTT for direct connect, for calls that are directly connected through peer-to-peer, and relayed calls either through turn or our SFU. So the blue line is the cumulative distribution of RTTs for direct connect calls, and the green line is for the relayed calls, and the vertical dashed lines represent the averages. So we can see that we have made the RTT smaller by allowing direct connections to be established. We're going to see exactly by how much. So we didn't have enough data for all of the regions that we deploy our infrastructure. So we have omitted Oregon and Australia. So we have focused on North Virginia and Ireland. So direct connect calls in North Virginia are 22% shorter RTT, and in Ireland they have 30% shorter RTT. And we have also observed a difference depending on the region. So server relayed calls have 60% shorter RTT in Ireland than in North Virginia, and direct connect calls have 24% shorter RTT in Ireland than North Virginia. So upload bitrate, and so this is the cumulative distribution of the upload bitrates achieved by the clients. We have three categories there. We have the direct connect calls, which is the blue cumulative distribution. We have SFU relayed calls, which is the green cumulative distribution, and turn relayed calls, which is the red cumulative distribution. All of them, there are multiple observations that we can do. All of them achieve about the same averages. They're about 1.1 megabit per second. The turn relayed and the direct connect cumulative distributions exhibit similar behavior, very different behavior for the SFU relayed calls, and this is due to the congestion control and the simulcast, and the fact that we activate simulcast. Again, the same, we can see the same here. We have the same picture here, but this is for the download bitrate. Very similar behavior for the direct connect calls and the turn relayed calls. Much lower performance on the SFU relayed calls, because, as we mentioned earlier, if a participant is streaming 1.1 megabit per second, the receiver is not going to get 1.1 megabit. It's going to get much less, depending on the layout. So this is how this lower performance can be explained. So here, yes, 4 minutes. Yeah, thank you. I'm almost done. So this is a summary of all this. What's important to keep in mind here is that if you activate SFU conferencing features in one-on-one calls, you drop the call efficiency by a lot. So 52% efficiency in North Virginia and 6% efficiency in Ireland. So what this means is that clients are uploading, but receivers are not getting everything that's uploaded because of simulcast or RTCP termination, which is how we inject our congestion control into the loop. So it's really important not to enable conferencing features in one-on-one calls. So the conclusion, we have, by introducing this dynamic switching mode, we have reduced our bandwidth usage by 52%. The infrastructure pressure has been reduced by 35 to 40%, so less memory, less CPU, less load. We improved the RTT by 20 to 30%, depending on the region. The throughput has remained more or less the same, so this hasn't changed much. Yeah, the group calling features reduce one-on-one call throughput efficiency by a lot, so the efficiency is pretty low if you have conferencing features. So that's my presentation. Thank you very much for being here. Let me know if you have any questions.